Welcome back. It's been a while. About a month, I think. Sort of left a bit of a gap. I kept meaning to come back to this and I kept putting it off. But we are still on problem 16 and should be able to finish it off now. So I was going around in circles with 16, not making much progress with part 2. I was definitely going down the wrong path. And I realized it at the time, but I mean, I needed to refresh my head, look at it from a different angle. And I kind of did, so let's try and reason that out now. Day 16 taking a whole month. Yeah, well, I only actually looked, even though I said I was going to look at it before, I only actually started looking at it today. I just procrastinated for a month, basically. Just get my coffee. So yeah, I'll probably just do 16 this stream and not anymore. I don't know how long that'll take. Because then I need to stitch all those hours of me banging my head against the wall together in one massive 7-hour YouTube video. Yay. Not that anyone's ever going to watch all that, but it's for okay, so it's for posterity. Let's remind ourselves. So we've got this, not 17, 16. This whole frequency transmission thing. It's a bit of a trap because it's sort of indicating if you don't actually look at your input, or you just look at the size of the input, but not actually look at the individual digits of your input, you would think that you're supposed to actually fully transform the entire 6 million long message each time. And you would be correct in thinking that, because for a general input, you would need to do that. I don't see any way around that. It's like every element. So you do this FFT process 100 times independently. Each time you do one iteration of FFT, each new element of the list relies on a sum of the entire list. So you can't get away with skipping stuff here. You would actually have to compute all 6 million every time. So for the general case, this is basically impossible in a reasonable time frame. I'm talking like trillions of operations. And that's what and all the optimizations I was doing before was getting closer, but I don't realistically see it getting anywhere. Anyway, when you actually look at the input, see these sample inputs, even these sample inputs are misleading. If we look at the actual input they gave us, this one here. So they said the first 7 digits of your signal represents the offset. So that's what position in your list you're going to use, right? So we look what those 7 digits are. 1, 2, 3, 4, 5, 6, 7. So 5.9 million, basically. Well, our list is already 6.1 million or something like that. So it's almost right at the end of the list. Okay, so that's a key property of this input, which is it's not in the middle of the list, it's not near the beginning of the list, it's right at the end. Why does that matter? Well, let's draw a diagram. Let's get paint graphics up. And I'm guessing everyone's input is somewhere towards the end of the list. Oh, forgot to put the music on. I'm gonna have to find some new no copyright chill out music. I can't keep using the same YouTube video over and over again. All right, so all right. Oh, it's not even playing. There we go. Okay. So, paint. Can make it a bit thicker. This calligraphy, just like a marker. No, just like a normal, just a pencil, but okay, brush is the right. Yeah, okay. All right, so what do we have? We have a sequence. Okay. And it is of length 650. All right. But they're saying you actually construct a larger sequence, which is this 10,000 times. Okay. All right. So the whole list, if you just forget about the fact that there is repetition here, if for all intents and purposes we just have some list which is 6.1 million long. 6.5 million long. Okay. And I was tempted to conserve the property that there's repetition here, but you don't need to do that because, you know, in the next iteration that'll no longer be true. So just forget about that. It's now a list of a random assortment of digits, 6.5 long. Now, in one iteration, we go element by element, and for one element, let's say index I, we basically do the dot product of this whole list with this other sequence they've given us, which goes like this. It goes 0s, 0, 0. Just a sequence of zeros, and how many? There will be I of these. And then there'll be I plus 1 ones. And then you get I plus 1 zeros. And then finally you got I plus 1 minus ones. So the I plus 1 of each, except you knock off the first 0, I guess, just to remove some symmetry there. Alright, so... And then finally, it just repeats from back to the beginning again. Okay. So, like, example, I equals 0, the very first element. There'll be no zeros. There'll be 1, 1, then a 0, then a minus 1, then a 0, then a 1, 0, minus 1, 0. So you would sum the first element, you'd subtract the third, you'd add the fifth, and so on. Okay. So it would look like you'd have to do a lot of work there. And that's true. But for big values of I, in fact, if I is more than half this list, you actually don't end up using most of these. You never go further than here. So the sequence actually just looks like this. If we're assuming I is bigger than, more than halfway through the list, then the numbers, this 0, 1 chain becomes so stretched out that it actually just looks like this. You got I zeros. And then you've got ones all the way to the end of the list. So basically, you're just summing up the final like suffix of the list, including your own element. Like if I is like 4 from the end, if we're looking at this element here, then this will become the sum of that plus the next 3 items, right? It would just literally just be the prefix, the suffix sum of the list starting from that element. That's easy to compute, right? So in one iteration, and we know that we only care about the tail of this list. We don't worry about, and everything in this tail only relies on what's to the right of it. So we never actually have to check that all these zeros are here. So we never actually have to sum in any of these first elements. So that means in each iteration, we only ever need to keep the tail of this list. So we're restricted to the final. All right. So what are the actual numbers here? So it's 5.9 million basically. So we want roughly the final. It's more like 6 million. All right, let's say the final 500,000 is the only part of the list we ever keep. Everything before that we can just discard altogether. We never touch it again. Because the index we want is in there. So in each iteration we only touch this tail and update it each time, okay? And what do we do in one iteration? We just start from the end, so we work backwards through the i's instead of starting from the beginning, like is what my algorithm is doing. Start from the end. So for I being at the very end, the sum is just the trivial sum, which is just the element itself. And the next one you keep a cumulative total and you add the second from last in and put that in, and so on. No more worrying about periodic sequences and blocks and anything like this. It's just a cumulative prefix sum. You do one sweep. It will take 500,000 amount of effort in one iteration. You do that 100 times. The amount of work you do is 50 million. Now that's still a big number, but it's doable. That's fine. We're talking minutes here, if even that. Clear? Don't know. I guess I'll have to code it and see. That is basically what I scribbled on paper here. Okay. So we go back to the code. So we have code here. Does it still work? Okay, first of all these to-dos, wow, I really set myself a lot of work, didn't I? We're not doing any of that. If this still works, I'll leave it as is for part 1. Let's check. So I've got the input. Yeah, okay, let's run it on part 1. Okay, block part 2. 4409. Is that correct? Yes, okay, good. That's a working part 1. In fact, it's faster. All this stuff I did actually made it faster than it originally was. So I did actually have some good optimizations there. It just wasn't enough to actually crack this whole thing. Alright, so part 2, in fact, we're not keeping any of this. Alright, part 2. Let's say total sequence equals let's say it's like this, and for do this okay, so it doesn't matter if we just construct this massive thing. There's probably optimizations we could do to avoid doing this, but it's we can do it once. So total sequence plus equal so that should just be have like 6 million or so. Right. So we've got our sequence. Now, we don't need to worry about blocks anymore. That's our sequence. The offset, we extract from there. I mean, just call it sequence. Print the offset. So that should be 5.9 million or something. Ah. No, we're not doing blocks anymore. 5.97 million. Alright. So the tail would be... I've got to get the index correct here. So it's going to be sequence minus... So what exactly did they mean by... They weren't zero indexing, so they were saying... They were saying that offset is how many digits you skip before you get to the digit you want. So if, for example, the offset was 6.5 million, then you skip the whole thing and that doesn't make sense. If it was 6499999, then you would want the last element. So you would want, basically we want minus length of sequence, which is 6 million, minus, well, okay, we can do the other way around, do offset minus length of sequence. Is that correct? So the numbers again. If that was 64999 and that is 65000, and you do that minus that, you get -1. And -1 onwards would be just the last element. Is that all correct? Yeah. So this is the tail. And the element we want is the first element of this list, except we have to process it 100 times now. Okay, that's a good start. And when we actually get the message out, we might as well just do this code now, because it's right here. It'll be for x in, it's going to be tail. The first 8 digits, right? Because that's what we've got. So let's just print that now. It will print something. That's after doing 0 iterations. That is the number. Right. 995571. So that's somewhere in there. In fact, we can do a Control F. There it is. Is that the right? 622. Because modular arithmetic. So yeah, it would be there. In fact, we shouldn't really... If we're being really efficient, we wouldn't actually construct that massive thing. We would just do modulo. Should we do that just to be extra efficient for no particular reason? No. We have to because we do need to keep 500,000 elements, so we do need to run through that 650 many times. Don't worry about it. Okay, so now take that out. So now we do 100 times. We do this process here. So what is it we're doing? We want the suffix sum equals 0. So we're keeping a running total. So how long is this tail? For okay, so for j in range, so we start from -1, which is the last element. We move backwards. And until we get to 0, which is the same as saying minus length of tail. But we want to actually process that one, so we have to do an extra -1 because we finish on minus length of tail. And we're going backwards, so we -1 each time. Alright, so we're starting from the end. We're saying so suffix sum plus equal tail. Okay. We need a temp tail. Because we don't want to change tail in place, because everything should be using the original state. So temp tail equals none for just an empty tail. All right. Tail j. So we add that element to the suffix sum, and then we put suffix sum into the temp tail in that place. Temp tail j equals suffix sum. So when j on the first j, which is going to be -1, we're just taking the last element and we're just putting it in temp tail. The last element actually never changes. That's a fixed point. And then for -2, well, we're accumulating this sum. So we're adding the next element along here. Putting that in there. All right. So once we've done that, we just say we discard the original tail. Tail equals temp tail. So it's about 500,000 amount of work. It's linear time, not quadratic time. If you were to do an actual sum, use the actual sum command for each of these j's, you'd be doing quadratic time. That would actually take too long. So you do need to have some smart optimization. This is a linear time suffix sum. Now what? So that's it? Would that just... Then we just print the first 8 characters of this? Alright. It'll take a while though, but... I mean, we could print the count of where we're at. Oh, it's done. Alright, that doesn't look right. Oh, because I'm not doing the right calculation. Hang on. It's not... You don't just add the numbers. Let me go back to the original thing. You... multiply every value by the pattern. Add everything up. Then you keep only the ones digit. Whether it's, regardless of whether it's negative or positive. So you make it positive, and then take the units. Then you won't have this massive number. Okay. So it's... So we keep the sum, keep the whole thing in the sum, but the moment we put it into the temp tail, we want to do absolute value and then just mod out 10 to get the units. So it's only ever single digits. Should actually be quicker now because then you're not storing massive numbers. 124822168. Could that be it? Oh my god. That's right. It only took a month. At this rate, we won't be done in time for Christmas. Oh man. That was a very good problem, and I mean, I knew everything I was doing was overcomplicated. The problems never go into as much depth as I was trying to calculate before, but it's just, at the same time, I just couldn't see what the trick is. The problem was I was hung up on this general case. You got to remember that although the questions in these are phrased as if he wants you to solve the general case for any input of a certain size, the reality is he's often giving you quite specific niche groups of inputs that follow certain properties, have certain sizes, and so on. So, as tempting as it may be to create a general case problem that will solve any input, it's not. Sometimes it's not actually possible. You gotta actually look at the input. So it's not like a lot of these competition sites, they don't even show you the input. You're supposed to provide the program. You upload the program, like Google CodeJam, for example. You upload the program. They tell you what the sizes of the input are. So they'll say, okay, it's gonna be between this and 1 million or something. But beyond that, they won't tell you anything like, oh, the first 7 digits will be this and so on. So you just have to make it solve the general case, and then they literally run it against 1,000 different randomly generated cases, and that's how those work. This is different though. This is like, you got to tailor your solutions to the input. It's quite clever, and I've been trained not to do that, so I gotta got to remember that for next time, because this does come up every now and then. But yeah, man, I was going down such a... Could I have even got there with the approach I was taking? I felt like, because I wrote all those to-dos at the end, I felt like it all worked mathematically, but I think there might have been some more pitfalls that I hadn't thought about. But there's no reason to do something more complex when just do what you're asked for and nothing more. I mean, this highlights a very, very important thing that you actually have to think about when you actually work for a company as a software engineer. It's so tempting, especially when you come straight out of university, to want to, you know, make a perfect program that solves a general case, which handles, you know, large-scale inputs that probably will never happen, and so on. But the goal... You know, the goal of the job is to make money for the company, and you make money by just doing the bare minimum. Always. All these big companies, Google, Amazon, I mean, I worked at Amazon. It's just everywhere. Shortcuts, bare minimum, everywhere. We're never actually making golden products which are actually, from a mathematical perspective, like beautiful pieces of code. All held together with duct tape, and it all just about works. We just put in the minimum required effort to make it work, and then leave it at that. That's all that happens. Good enough to make billions, yeah. Yeah, I mean, and of course it depends on the industry. Like, there's some industries like healthcare where the bare minimum is not good enough. Maybe like aviation would be another one where the bare minimum is not good enough, and that's of course a big topic right now. Boeing and all that. So, you know, if you're writing software for aviation, writing software for the medicine industry, you do actually want to write for the perfect... You do actually want to write for the perfect case, the cases that never happen, but they may happen once in a million times. But yeah, if like me, you were just making a Netflix competitor, it really doesn't matter even if the site goes down at some point. You know, people will live without their movies for an hour. Although, if the site does go down, that is actually... Sev1 emergency. So whenever I raised issues in the bug system, I had to choose from a drop-down the severity. There's Sev1, which is the worst, and Sev5, which is the least. You know, Sev5 is just like, oh, this button is the wrong color or something, and Sev1 is like, you know, the website is down, or I've seen a Sev1 in the system, our office is flooded, and we can't get into the office. That was actually a Sev1. But, whenever I were to enter a bug into the system, I had to choose the severity from the drop-down. I lived in fear every day that one day I might accidentally click Sev1. It's just a normal drop-down. You could just click Sev1, but then you'd have to confirm. But still, if you were to click Sev1 and confirm, you would ping every single Amazon employee everywhere in the world, including Jeff Bezos himself. Even if Bezos was sleeping, he would be woken up and have to attend to it. Yeah, I constantly lived in fear that I might accidentally one day do that. And for developers, it's not grayed out. Sev1 and Sev2 are grayed out for most employees for that reason. But we developers have full access. We have to. You can't get anything done without having that much power. So it could have happened. Personally fired by Bezos, yeah. I don't know what would happen in that case. I mean, it was obviously an accident, but it's also... You've also cost the company a lot of money. Alright. well, I think how many hours of yeah, we'll just have to leave the stream there then, because I've now got to stitch these videos together. So let me have a look at my stored videos. We've got 2.5 hours, then another 1.5 hour. Four hours. Oh, it's only 4 hours, and then this session was half an hour. Oh, it's only 4.5 hours. That's less than I spend on, like, video games in one session. Alright, well, anyway, I'll still do that. So, Advent of Code will be back, maybe even tomorrow, 17 onwards. And yeah, I'll just stitch the video together. I mean, the editing, I don't edit anything out. I will leave all hours of me just staring into space in for posterity, but it will take hours to actually render. Can take a sneak peek at 17. What is 17? Solar Flare. Oh god, RimWorld. Oh, it's an of course it's an int problem. Every odd numbered problem in this year, in this month, was an int code problem. Do I remember? Well, we've still got the int code script at least. Doesn't look too scary. Something to do with positioning in a 2D grid or something. Alright, well, I might come back later with what game is in rotation now. Discworld or RimWorld? What do I feel more like? Probably like maybe an hour of Discworld and then just RimWorld all night long. I don't know. We'll see. Alright. See you next time. DRJ. Bye bye.